we'll have a talk by Matias, and Matias is a researcher at the DFKI, or the German Research Center for Artificial Intelligence. And funnily, actually, I saw that his most cited publication is actually real-time convolutional neural networks for emotion and gender classification. I think that would actually also make a great talk, but maybe for another time, because tonight Matias will talk about uncertainty quantification in computer vision and robotics. And as usual, we will also have a Q&A after the talk, and we will be using Slido again to collect some questions. And at the end, we will also have a networking session. We'll be using Water again. For those of you who have been participated in prior events, you probably already know. Yeah, we use Slido, and here is the link and the event code for the Slido session. We also send around the links previously in our emails. And I would actually invite you already to open Slido now already, because already during the talk, you can start asking questions. And this will also give people more time to actually vote on questions. However, please note that we will just be discussing the questions after the talk, because in the online meetups, it's quite difficult to have a good way to interact with the speaker during the talk. And so for that reason, add the questions that you have already or during the talk. Then there will be some time for asking questions and voting. And in the Q&A session, we will be discussing the most upvoted questions. And we will also share the links in the chat. Then, as usual, also feel free to talk about the meetups on social media. For example, we are trying to be active on Twitter, so use the hashtag CAIML, or our account is CloneAIML. So please help us spread the word. And now I would actually pass on the word to Matias for his talk. And yeah, enjoy the talk, and see you later in the Q&A session.
Perfect. So let me share my screen. Here it is. So you can see my slides now, right?
Yes.
Yes.
Perfect. So first of all, thank you for inviting me. It's a great way to see people connecting in the Cologne-Bonn area. So that's where I did my master's at the Hochschule Bonn-Rhein-Sieg. And right now I'm working at the German Research Center for Artificial Intelligence in Bremen. So my talk is going to be mostly three parts. First, I'm going to give you like a short introduction to what we mean about uncertainty quantification in the context of machine learning. Then I'm going to talk about a bit how uncertainty should be modeled in robotics. So it's more of a forward-thinking part. And then I will tell you about what I have done in terms of uncertainty quantification research.
Sorry to interrupt. Please, could you speak a little bit slower?
Sure.
Thank you.
I always try to do that. So let's start with introduction to uncertainty in machine learning. So let's imagine that we have a training set, dogs and cats, and we train a classifier. So this is like a very normal benchmark data set, and you have a trained model. So what happens if you have this trained model and you test it with a human label, with a human image like the one we have right here, or we test it with an image that has both a dog and a cat? So what autoprobabilities makes sense in this case? So if we think the model was only trained for two classes, for dog and cat, if you test it for a human, of course, it should not output either dog or cat. But if you use like a common known machine learning model, like a neural network or a convolutional neural network, they will give you either dog or cat with a very high confidence or probability. And if you give it dog and cat, it will probably also give you one of the classes, but not both of them. So what does it mean to be uncertain here is that the autoprobabilities of the model should make sense for a human and should represent more than just a classification result. Like just more than you say dog or cat. Can you also say, for example, the model cannot say, I don't know? And for this, we usually relate this to the concept of entropy, because the entropy is one way to measure the uncertainty of or the energy of of a probability distribution. So for example, ideally, if you have a model trained on dogs and cats, but tested on a human, it should output 50% cat and 50% dog exactly. And then when you take the argmax to decide which class, basically you should get an error because both probabilities are equally likely. And this should signal you that there's something wrong in the input. And the same if you have a dog and a cat, you should get equal probabilities because the model was not really trained for both classes. But for example, if you have an object detection model, then you can output both classes independently. But that's because the model itself is designed for this. So also we look at these images, and these are images from the FAIR Plus dataset that have what they call crowdsourced labels for emotion recognition. So this is from the paper that Fabian mentioned at the beginning. So we didn't make this dataset, but we are using it for different benchmark tasks. So if you look at the images, one is labeled with happiness, other with anger, and the last one with neutral. And here I put a representation of the probability distribution for the classes, and the classes are over here, neutral, happiness, and so on. And as you see, visually, it's very ambiguous which class is let's say, is the correct class for each of them. For example, in the first example, some of them say it's neutral, most of them say it's happiness, some people say it's anger, and some people say it's disgust, I think. And the same for the other classes. So here is that you need to have a model. You cannot use a simple machine learning model because these models usually don't really quantify uncertainty correctly. For this task where you have a lot of, let's say, input uncertainty, there's a lot of ambiguity in the model, in the data. And then you also need to consider maybe there's more than one class that is actually positive at the same time, depending on, of course, of like, let's say, human opinion. So what we mean by uncertainty in machine learning is that, well, real-world data sets are also generally unbalanced. You have different numbers of samples per class. So the confidence on each class should be different, should reflect what the model infers from the training data. And also real-world data sets have noise, like, for example, imprecise labels, ambiguous measurements, or sensor noise. And a model should be completely aware of this. In general, models are not very aware that the sensors, of course, are imperfect. And finally, most neural networks are overconfident. This means that the confidence you get from a softmax function are not a very good probability interpretation. Like I mentioned, the example of dog versus cat without human input. If you use a softmax without any kind of uncertainty quantification, you will get misleading probabilities. And this is what people mean by overconfident in literature. So what is lacking in classical models? What is first is that classical machine learning models, like all models without Bayesian, let's say, interpretation or a Bayesian neural network, don't really explicit model uncertainty at the output. So they produce what is called a point-wise prediction. And this is much easier to see in a regression setting, where instead of having a probability distribution as the output, you only get one value. And a model that outputs a probability distribution is a model with uncertainty. So distribution includes a lot more information than just a single point-wise prediction. For example, you can have a prediction that is the mean and the variance for a regression output instead of just one value. And then the model is telling you that, okay, I think this is the right value, like in the middle, plus some spread or plus some error that the model can build by itself. And as I mentioned, neural networks usually are overconfident, and this means producing wrong predictions with high confidence. And of course, we don't want to have that because the confidences in a model are what some people interpret from the model. Like the confidence should make sense for a human. In general sense, they don't make much sense. And here I have an example using well, the green points are the training set. The ground truth training set. The function is actually x to the power of 3 plus some noise. So the noise varies with the input. And you have the mean of the ground truth in the red line. And here we have 3 blue levels, which are models that output uncertainty. And this is the 1 to 3 sigma confidence intervals. And one important thing is that the training set here goes from -4 to 4. Outside of this range, there is no training points. So all the training data is between this range. And And of course, the model cannot extrapolate outside of this range because it has never been trained for this, right? So you can see that from the point of -4, like there is a mismatch between what the model produces and what the ground truth says. Like the blue shaded area goes outside of the green points, and this is the mismatch. But the variance in the output or the standard deviation, which is represented by these confidence intervals, actually tells you that there's something, let's say, wrong. And as you see, the variance increases as you move outside of this range. And this is exactly what we want. And I will show you more examples about this, but this is one very simple case in regression where you can see what is the advantage of having model uncertainty. And some practical applications of if we had models that can correctly estimate an uncertainty. Once, if you have a reliable confidence estimate, you can detect misclassified samples on when the model is extrapolating. And for example, for things like medical applications, you actually want this. You want the medical doctor wants to know if the model is working, let's say, in its training regime or is extrapolating, basically, if it's guessing. Because if the model is guessing, then the medical doctor can use this information to maybe make a second test or maybe make a human decide on this image if the model cannot do it. Also, a model can reject to produce an output if the uncertainty is too high, as I mentioned, to require human processing instead of being automated. And this is called out-of-distribution detection. So the confidence or uncertainty of a prediction tells the human how much you should really trust. And this should be what is said calibrated. So we will mention this in a few slides. Yeah. So there are two types of basic uncertainty measurements. One is allatoric uncertainty, which is the uncertainty that is inherent to the data. For example, sensor noise, stochastic processes that generate the noise. So this data cannot be reduced if you add more information. For example, if you gather more data with a sensor, this data will also have the same kind of noise. So you cannot really reduce this uncertainty with more data. While on the contrary, there is epistemic uncertainty, which is uncertainty that is produced by the model. For example, if you specify the incorrect model, and this is called model misspecification. If there's class imbalance, there's lack of training data, for example, for some classes. And unlike allatoric uncertainty, epistemic uncertainty can be reduced by adding more information to the training process. Like if you have a class that has less samples, then this will be more uncertain, but you can fix this by adding more samples of this class. And here I have an example of allatoric uncertainty. So for example, you have measurements that are corrupted by some additive noise, like x to the power of 3 plus some Gaussian noise. You can measure, make your measurements, but it's very difficult to find the true function that is actually generating the data, because there's noise that is corrupting your data, and you don't know if the true function is related to the noise or is independent. And one important detail is that if you have the variance of the noise, if it's constant, this is called homocedatic noise, and you can see it here in the left plot. But if the variance of the noise is a function of the input or variable, or if it's variable due to some other reason, this is called heterocedatic noise. And this is also complicated because then a model may also not assume that the data has a constant noise or it's variable. And then, of course, if it's variable, the model should also be able to predict this, or to be aware that the noise may be variable. An epistemic uncertainty is much more easy to think about. One is model misspecification. So for example, I have here in the left plot some blue points, which represent some unknown function plus some noise. And here I plotted several curves that are trying to fit the model, because we don't know what is the true model in this case. So basically we try a linear model, two linear models, a quadratic function, an exponential function. And not knowing what is the, let's say, the right model or the right equation produces epistemic uncertainty. Because of course, if the model doesn't fit the data, then this produces epistemic uncertainty by definition. And there's also what variations are possible in the training data. So here I have a plot that one of my students produced in his master thesis. And it has in the x-axis the number of samples, and in the y-axis the entropy. So you see that these are different classes, and this is from the kitty dataset. And this is the uncertainty to what one model produces, that the less samples that a class has, the higher the entropy, meaning that the higher the uncertainty. So for example, motorcyclist has 10 to the 5 samples, which is quite less compared to other classes, and it has the highest entropy of all the classes. So this is exactly what I mean by epistemic uncertainty, that the lack of data basically produces more uncertainty in the model, and the model should be able to estimate this, to produce different confidences that in the end traduce to or translate to what the user will interpret. And of course, one of the best methods to produce uncertainty in a neural network is what is called the Bayesian neural network. So here I have only one slide about this because it's a complex concept to understand, and of course the questions are also complex. But the difference is in that in a Bayesian neural network, the weights are probability distributions instead of being just scalar weights, instead of being point estimates. So you have weight distributions that encode uncertainty in the network. And of course, to make inference on this, like to make training and predictions, you need radically different algorithms using probability and Bayesian frameworks and bias rules, of course. So here I will include how to compute the predictive posterior for the Bayesian neural network from inputs. And it's basically the integral over the parameters theta of the probability of one output given the input and given the parameters theta multiplied by the probability of these parameters theta and then integrated over all theta. And the problem is that computing this is very computationally inefficient or even intractable because you're basically integrating over the whole real numbers. And even if you have the distribution of the weights after training, you need to compute this integral for every input sample. So this is completely computationally intractable. So this is why we don't really use Bayesian neural networks and why we need to do approximations. So this is called Bayesian model averaging because it's basically taking the average between multiple models, and each model is the same structure, but it has different weights, and the weights come from this probability distribution. But the nice thing is that it automatically outputs a probability distribution instead of being a single data point or a single point estimate. And now I'm going to finish the part about the introduction with calibration. So I mentioned a concept that we need to trust or to have a number of how much can we trust the confidence of a model. And this can be formalized mathematically by comparing the task performance, for example, accuracy, as the confidence of the predictions change. Like if you have a prediction that has 10% confidence, then a human expects that the prediction will be correct only 10% of the time. And it should not be correct, for example, 30% or 50% of the time, because then that means that the confidence is not correct. And of course, if you make a prediction with 90% confidence, then only 10% of those predictions will be incorrect, and 90% will be correct, right? So this is how it should work, but of course, that's not how it always works. I will mention some examples here. So you can observe or measure calibration using what is called a reliability plot. So you take the predictions of a model over a data set, and you take the class predictions and the confidences for each class, and you divide the predictions by confidence into bins. Each bin, well, it's the same as a histogram. And for each bin, you compute the accuracy, like what percentage of the predictions are correct in this bin, and this bin represents some range of confidence. And then you plot the values of confidences and accuracies in a plot. So there are three kinds of regions. One, when the confidence is less than the accuracy. So this indicates that the model is underconfident in this part. There are regions where the confidence is larger than the accuracy, which indicates overconfidence. And the line where the confidence and the accuracy exactly match, this indicates perfect calibration. This is when you can actually trust that the confidence of predictions actually tells you, or that you can use it to predict when the model is going to be incorrect or not. So you can see them here. So here I put in the top part two plots. One is for an overconfident model, which is below this line, and one for the underconfident model, which is above the line in the middle. And the line in the middle represents perfect calibration. So these methods are, and you can compute metrics over these methods, like compute mean square error or a weighted error and so on. But the important thing is that if you plot this for any model, usually you get either an underconfident model or an overconfident model. And in order to get a calibrated model, you need to use you can calibrate the model manually using things like flat scaling and so on. Or you can use a Bayesian neural network or an approximation, which automatically it's kind of calibrated. So now we will talk about how all of this applies to robotics in general. So for this, I will describe research that is not my research, but it's a very nice paper from Nico Sonderhoff. That the paper is called The Limits and Potentials of Deep Learning for Robotics. And they discuss what are the, let's say, missing areas or missing examples in robotics that can be filled using deep learning. Because one thing is the field of machine learning and deep learning and computer vision, where we usually mostly do evaluation on data sets. But this is very different from robotics, where we usually need to do evaluation on the robot itself, because the robot has a body, while let's say the agent in machine or deep learning or in computer vision doesn't really have a body, like a camera doesn't have a body that it can use to interact with an environment. So as I mentioned, the embodiment is the main difference between robot learning and the other more theoretical fields. So in this paper, they provide this kind of orthogonal representation. One is reasoning, one is learning, one is embodiment. And I would like to put some effort into, or emphasis into learning, because in learning, you see the first level is uncertainty estimation, then to identify unknowns, to do incremental learning, then to do class incremental learning, and at the end, do full active learning. So this is from the paper directly. So if we go to the level 0, that's the level that we are currently are. So most machine learning systems are at this level, that you can detect and classify objects, but you know which classes you want to detect. You are not aware that maybe there were new classes that you were not able to detect, and it usually provides uncalibrated confidence scores. At level 1, you have uncertainty estimation when you have epistemic uncertainty quantification, for example, current work on Bayesian deep learning. Then at level 2, you can identify unknowns in an open set scenario. The robot can actually identify that some classes are new. And after that, you can do what is called incremental learning. You can learn new instances of known classes. And as we move across the levels, you can see that this is much more difficult, because like most research now is between level 0 and 1. And once you move, for example, to level 3, you get something that is almost impossible currently to do class incremental learning, meaning that you identify a new class, you learn new classes, but you don't let's say forget about your previous classes. And the last level is to do full active learning, to be continuously learning from the environment. So what kind of challenges and applications we get here in machine learning is, one is medical systems and decision making. So I think it's a legal requirement, for example, with the GDPR, that you have an explanation and you need to have uncertainty for that explanation. And also for robotics. So useful uncertainties in robotics are not really modeled. For example, uncertainty in dynamical systems, in perception, or to estimate when the robot is being extrapolated. So I think the best example for this is autonomous driving, that if we had autonomous driving with correct uncertainty quantification, then maybe the robot will be much more conservative to drive in roads where it's not really sure about what the robot is actually seeing. And of course, one big challenge is to use this in reinforcement learning. So have policies that you with reinforcement learning that can estimate their own epistemic uncertainty and not take actions when the environment is too different from the training one. Like when the robot is not sure, and reinforcement learning is very used for robotics currently. So for example, to do reinforcement learning in real robots or mechanisms with safety constraints, and do reinforcement learning in non-stationary environments, for example, with the dynamic or unpredictable obstacles, and to reduce the sample complexity through active learning or exploration. So the objective as a long-term thing is that you have a robot that actually thinks about what it's doing, or at least it can say that it can do something. Because, for example, if you ask the robot to do something that is very far from the training set, the robot should be able to tell you that, okay, this is very far from my training set, so it's very likely that I will make a mistake. So maybe I should not be doing that. And I represent this by this HAL 9000 that I'm sorry, I'm afraid I can't do that. And we actually want robots that can do this, right? But I don't think that that's something we have right now. So some examples that, well, there are multiple incidents of autonomous vehicles by different companies that have hit humans and killed them. And of course, this is not good. Because there are conditions that are not considered in development training. Like, for example, there's one example, I don't remember which company, that hit a person that was crossing the sidewalk because the person actually looked very funny, like he had clothes that were not conventional and so on. And that kind of stuff should not happen. And the same, for example, at care homes, you should have algorithms that are tuned for maximum safety, right? Also, if you have face recognition systems that are biased against some skin colors, auto-decision detection can help in preventing this. Like the model will tell you, yeah, actually, I cannot classify this kind of skin, instead of trying to predict something that some people may find offensive. So here I have a very simple example. So here I have a model that I trained on MNIST. And you see on top of each of the images, you see the images with the largest entropy and the smallest entropy. And entropy is a measure of uncertainty. So the largest entropy, the more uncertain the model is. And you see in MNIST that the model, the digits with the highest entropy are the ones that are, of course, more difficult to classify. So this was trained with an ensemble of models. So for example, this is the first example is a 3, but it kind of looks like an 8 or even a 9. So depending on how you interpret the strokes, it can be different, and so on. So these are the examples, of course, of the model things that are more difficult. And now in Fashion MNIST, so I trained the model on MNIST, but I evaluated on Fashion MNIST because the images are the same format and the same dimensions. But of course, if you train a model on MNIST, it should not work with any of the images in Fashion MNIST because the classes are different, right? So of course, all the examples are misclassified. But if you look at the entropy that the model produces, there are some very good examples that, for example, these pants, they have the highest entropy, and overall, most of the examples have very high entropy. So you can use the entropy to detect that that the model is actually extrapolating or is operating outside of its range, given the input. But of course, there are some examples, like the ones in the bottom row, that have 0 entropy, that the model actually made a very confident prediction, even if this prediction was incorrect. So that also means that this method is, of course, not infallible, but at least it shows one possible direction in this research. And here I have an example with the sinusoid. So it's a sinusoid with noise. And you have the confidence intervals here. And I mentioned here that the training study is from -8 to 8. And you can observe that outside of that range, the uncertainty basically explodes, like increases linearly with the distance to this range. And so you can use this the value of the standard deviation to decide if it's a low value, okay, it's inside the training set, everything is okay. But if it's high, like something like more than, I don't know, 0.5 or increasing, you declare that the model actually, the input is outside of the training set, and then maybe a human should operate the robot instead of letting the robot operate by itself. But this is, of course, a very simple example. And now I will go into my own research into uncertainty quantification. So one of the best methods to do uncertainty quantification now is ensembles. If you have an ensemble of neural networks, basically copies of the same model, but you train each model independently, you still get a very powerful method to estimate uncertainty. But of course, now you need to make multiple forward passes of a model to make one prediction. So it's more computationally expensive. But then I asked a basic question: is it really necessary that all the ensemble members are independent? Like, can you share weights between ensemble members? And the answer is actually no. You don't need to that all the ensembles need to be independent. And by sharing weights, you can actually save computation. And I mentioned this as this example. I have on the left the classical ensemble, and in the right the sub-ensemble. And the classical ensemble, you have only different copies of the model, and in the sub-ensemble you have this TF, which is which I call the trunk network, which is one let's say network from the input until to some layer in the middle, where this is shared by all the ensemble members, and these Ks, which are called task networks, which are the ones that are actually ensembled and go from the middle of the network to the end. And then you combine these outputs, usually take the mean of the predictions, and then this usually produces, you can estimate a mean and a variance, or for classification, you use estimate the mean probability vector. And this actually works really well. So here I have different combinations. So DE is the original ensemble, and SE is the sub-ensemble with different configurations, like ensembling one layer at the end or assembling 2 layers at the end on 3 datasets, on MNIST, Cypher 10, and SVHN. And you actually see that that the sub-ensemble works as an approximation. So you lose some accuracy. So the error is slightly higher, but usually it's like 2% less error. But then this is much faster, like 5 to 10 faster than in terms of computational performance than the original ensemble. And that's the idea, that if you have a method that you can estimate uncertainty and also be not computationally that expensive, you can use it for real world applications. Because of course, in real world applications, we need to care about computational performance. So there's also the one plot that I got from the thesis of Maria Martin, which was also under my supervision. So we basically tried models with uncertainty for the emotion classification problem. So here you have images of the FAIR plus data set. You have in the second column the true labels. So these are probability distributions. And we compared the probabilities made by a classical neural network and with a classical neural network with uncertainty. So it's also an ensemble of dense nets, if I remember correctly. And overall, the model with uncertainty actually models much better the probabilities. They're much closer to the true labels, even if there's quite distance between them. So for example, the model always confuses some of the probability distribution is way more flat than the true labels. But this shows you that for this kind of problems, when there's high Allatoric uncertainty, then you should always use a model with uncertainty and not a classical model. Also, I mentioned this plot that is from the thesis of Swarup Bandari, also from the Hawksville one, where we actually see that there's a linear relationship between the number of samples and the entropy. So more entropy means that there are less samples in the dataset for that class. And I think this also motivates that some classes are naturally more difficult to detect. For example, I think there's a lot of confusion between bicyclist, bike, person, and motorcyclist. And that makes sense for a human, but of course it's kind of dangerous because the classes that have the highest entropy all involve humans. They don't really involve inanimate things, like for example parking or roads. Like for roads, you can be very precise, but for things that are humans, usually are less precise, and this should worry actually people that want to have autonomous driving. So here I have a plot. I know that it's a bit complicated to understand because there are a lot of things. So we have two sets of plots. So we have the entropy on the right, the ground truth segmentation. So this is point cloud segmentation, and the predictions in the right. So you see, of course, that the predictions don't always match with the ground truth. But in some regions, you can actually see that in between, let's say, segmentation regions, the uncertainty usually is higher. But also there's a class that is, I think, is unlabeled, which is kind of dark color, and some where it's basically anything. And usually these are the regions that have the highest uncertainty. So this, if you analyze this in detail, you can see that that we need to have models with uncertainty in order to prevent, let's say, predictions in places where there's no data, for example. Now we're coming to the end of the talk, so I have, I think, 3 more minutes. So one is that we're working with Octavio Arriaga, also a colleague from the Uni Bremen, about how to estimate difficulty on the training set. So for this, we had the idea that if you look at how the loss evolves for each sample in the train or the validation set, you can find if the model thinks that some examples are more difficult or less difficult. So here I have some examples in Cypher 10. So below each image, you have the class, the predicted class. No, it's not the predicted class, it's the ground truth class, and then the action score. And the action score is basically the sum of the loss for each sample across the whole training run, across epochs. So you see here, the first one is dog. It has an action score of 1,000 something. And below it's a horse. And if you look at you compare the horse and the dog in the first column, they're basically in the same pose. And I think the model has trouble saying that this is a dog and the other thing is a horse. So it's confusing these two classes. In the second column, you see this thing that is labeled as a cat, but it's actually a frog. And then you see this truck that is kind of in a very strange pose compared to the other trucks in the training set. Then the image D has a cat, and there's actually a cat, but it's very hard to see because the background is almost the same color as the cat and so on. So you can use this simple method to actually find the biases in your model. So I have another example here for object detection using the single-shot multi-pass detector on the Vox 2007 validation set. So here we actually look at the localization loss because you can look at the sum of losses for different components of the loss, like the localization loss, the positive loss, and negative loss. So for the first sample, you see there's a boat, and the boat is actually very, very small. There's a train in the second image, and this makes the model that it's very, very difficult for the model to actually localize these objects. And then this should tell you something about how your model is actually being trained. And if you look at the bottom row, we have all the objects that are very easy to classify. And of course, these objects are the ones that are, let's say, covered most of the image or all the image. And they're very easy to classify and to localize for the model. So you can see that the model has different biases in different parts. And now my latest paper that was accepted now at the CVPR 2021 workshops. So it's about lack of uncertainty in computer vision. So it's basically a meta review of what real world applications are using high quality uncertainty quantification, and there's probably not many. So I couldn't find papers actually describing real world applications of computer vision using uncertainty quantification. So here I also put some examples of failure cases. So for example, here you see a picture I took some years ago about Isano Konomiyaki. And we tested it on a mass car CNN model trained on Coco. And if you look at the labels, the okonomiyaki is detected as a bowl with a 75% confidence. The other okonomiyaki in the background is detected as a pizza, which, okay, makes sense, but of course is incorrect because the classes here do not match with the Coco classes. And there are some other, for example, there's a spoon on the left side that is detected as a fork and so on. So I think it's okay that a model has incorrect predictions, but what is not okay is that the confidences are very high. So for example, for the fork is 77%, something like that. So of course, this indicates that the model is not really estimating its own uncertainty correctly. And here I have two other examples. So this is also an image I took in Japan a few years ago. And this is the one in the left is trained on it's a very large data set made by Google. The Open Images data set. And it has two classes for dog. It has carnivorous and dog. But if you look at the confidences, it thinks that this dog is 44% dog and 61% carnivorous, which is kind of strange for us. Like, it should be more dog than carnivorous, right? And if you look at the other predictions, are all three predictions that are kind of all over the place. And if you look at the right, then you have a lot of incorrect predictions in this image that have high confidence. Like if you look at some of the labels, they say person, where of course there's only food. And there are a lot of bowls that, yeah, makes sense, but I'm not sure if I will call this bull. So now to close, so uncertainty is a very useful measure to detect misclassified and auto-distribution examples. So the literature confirms this, but of course, the big question is how do we apply this to real-world applications? Like the idea of my talk is to motivate you to actually use these models in real-world applications as a way to also estimate the limitations of the models. Because in general, Bayesian neural networks are not often used in practice, but there are approximations that we can use like an ensemble of neural networks. And robotics in particular is a great application field, for example, with Bayesian RL or probabilistic object detection. This is a field that is starting to develop in the last, let's say, 5 years. So I expect that there's an increased use of these techniques in practice. And that's all from my side. So now I can take questions.
Great, Matias. First of all, thank you. What I wanted to share is my screen containing the information on Slido. Here again is the link to the Slido tool where you can actually post questions. I already saw that people have started to add questions, and maybe let's give us 3 to 4 minutes time to vote on questions and to ask questions, and then we'll get back and go through the list of questions. Please.
So of course, the most difficult question is at the top. That's interesting. So yeah,
maybe we can just start now.
Yeah, I'm not sure how to write it with the bias variance trade-off because, and incredibly, I was teaching this today. So the bias variance trade-off is between the loss, right? And the loss also includes uncertainty somehow. Like you use the cross entropy. This also includes the confidences of the networks. So this is, of course, there's some relationship, but I also think it's difficult to say. So maybe there should be more research on this area. That maybe you have an additional axis that you have models that are very biased, but they have good uncertainty quantification methods. But also, for example, the variance in the bias variance trade is about overfitting. And usually, of course, models with uncertainty also overfit. But usually the difference is that sometimes you can detect overfitting with or failure to, let's say, to generalize with uncertainty part. And this is the kind of the extrapolation part. But yeah, it's difficult to find a direct relationship between these two things. So I don't think I can give you a satisfactory answer for that, unfortunately. But I definitely think it's an interesting question to see for the people that do theory in deep learning.
Maybe there's some students in the audience that want to write an upcoming master thesis. They can reach out to you.
Yes, for sure. So the second question is, which connections do you see between understanding explainability and understanding uncertainty? So that's actually very interesting. That's one of the things I wanted to see, because when you have an explanation, you usually have a classical method. And then one thing is that if you have a model with uncertainty, the explanations kind of also look very different. So I have some experiments, because you have an ensemble of models, or you use dropout, for example, with MC dropout. And then you're basically combining the explanations of multiple models. So usually the explanations are less noisy, but also the uncertainty at the output also tells you something about the model, which you can also kind of interpret. But there's also a new research direction that I think should be put more attention, and that is you have an explanation, and you can also have uncertainty on the explanation itself. So to make sure that, okay, the model that you're using for the explanation, be some kind of heat map or something else, you can also have an uncertainty of this, like how much should I trust this prediction, this explanation. I think that's also very, very interesting. But of course, I think there's also should be more research about how to connect uncertainty with explainability. Like maybe we can get additional information for explainability just from the uncertainty measurements. So the next question is an introduction tutorial for this topic. So actually, yes, I can show you a link, because last year I made a tutorial including code, including a framework that I made for uncertainty quantification, which is called Keras Uncertainty, which is in my GitHub repo. And I made a tutorial for the PyData Global Conference. So the video and the slides are online. So I think I will share them with Fabian, and he will share them with you probably.
Yeah, that would be great. I will then send them around tomorrow.
Yeah, but also I'm writing a paper about, like a kind of tutorial paper about uncertainty, because uncertainty in machine learning, because there's a lot of things, a lot of concepts that are kind of very new for a lot of people. And if you look at the literature, it's mostly going into the very theoretical direction. It's not useful, for example, for PhD students, because they have to read a lot of papers. So I'm also working on like having a decent tutorial that people can read, and I will probably put it in archive in the coming months. So what is the effect of augmentation on the difficulty score? Actually, we have the experiments on this. So we are writing a new newspaper right now about this. And the effect is, well, it doesn't really have an effect, because if we use data augmentation in terms that you create new samples, these new samples they always assign the action score to the original sample. So in reality, it doesn't even change the action score significantly. So is there an open source implementation? Yes. So as I mentioned, there's this Keras Uncertainty framework in my GitHub repo, which implements some of these uncertainty quantification methods. So it implements ensembles, dropout, and drop connect, which are both used for uncertainty quantification. So all of the samples I showed are using this framework. So of course, it's a very experimental framework, but it works. And so far, I have only implemented this using Keras. So the other question is for networks which work with heat mass as ground truth, like for example, I think segmentation. Can we rate uncertainty with the output? Well, if you have a segmentation network, you can also estimate uncertainty at the output. Like you get one uncertainty value for each pixel, and then you can get a heat map of the uncertainty on the image. So that also works quite well. So your opinion on neural networks solving this problem? Well, most of the stuff that we do right now are neural networks, right? So all the examples here I show are using neural networks, especially convolutional neural networks, because they're basically the state of the art for a lot of tasks. So yeah, my opinion is that we should definitely continue doing research on neural networks, but also not forget classical methods. So I think some of the methods that I mentioned have not really been evaluated or let's say extended to classical methods. For example, to have an SVM with uncertainty. I think that would be quite interesting, because even you can use SVM, for example, for transfer learning, and there are still and they're still being used in practice, especially if you have little data sets. So yeah, autonomous cars, not as confidence required, yes. So implications for society, well, I always been very skeptic about autonomous driving actually happening, because like we have currently autonomous driving cars, but they only work on certain situations, like for example in California, or in here in the US in Karlsruhe with the key detectors and so on. But of course, the question is, how do you make sure that there's a generalization, that they actually work on multiple scenarios, and when the car doesn't work on let's say, or cannot work in some scenario, then they actually tell you about it. So this is the relationship with uncertainty quantification, that you need to have models that use uncertainty in the car. And unfortunately, when I was writing my latest meta review paper, I was trying to find out which models are used by these autonomous cars, like by Tesla or by Uber and so on. And there is little information. So I think in terms of impact to society, we should have regulation that actually forces like the manufacturers to actually tell us what kind of models they're using, like some basic information at least, and probably make like proper uncertainty quantification mandatory. So that's how it should be, right? If the companies are not doing it by themselves, then regulation has to be enacted to make them work it. So yeah, and finally, so contact form after this. So yeah, I have my email address at the first slide. So we will share the slide, and then you can find my email address. Also, if you put my name in Google, you can easily find my website. So yeah, let me share maybe the first slide, because there are no more questions in slide. No?
Yeah, and maybe you can
so here's
share your screen again with the email address. Otherwise, I would also suggest that we definitely add that information, otherwise to the mail that we will be sending around to the meetup group, and so that everybody can find the information.